So, just a few more comments on this. So, also, Berger's theorem really lists what you could argue are the most interesting geometric structures in Riemannian geometry. Okay, so that's a bit of a value judgment you may not agree with, but so that is it classifies geometric structures that can be preserved by the Levi-Civitan action of a Riemannian metric. So Berger's, it kind of tells us that there's some interesting geometry in the various possibilities there. So in fact, we already knew about Kähler geometry before Berger, and maybe some of the other possibilities. The exceptional harmony groups G2 and spin 7, nobody knew about them until they popped up in Berger's classification. Okay, so, well, actually, Berger's theorem it doesn't say that the possibilities on the list are possible Lomé groups. So it just says that everything else is not possible. So Berger's theorem says that if you have a metric, then its Lomé group is one of these possibilities, but Berger didn't actually tell you that all of those possibilities can occur. And as we'll see, somehow the way Berger proved it is to make a list of all conceivable Lomé groups and then start chucking possibilities out until what's left is this list. Okay, so actually Berger included one more possibility, which is a potential Lomé group spin 9 acting on n equals 16, which is the Lomé group of a weird object called the Cayley projective plane. But the Cayley projective plane is a symmetric space, and in fact this can only be the Lomé group of symmetric metrics. But this was later excluded by Alek Zajewski. Possibly independently by a Brown as well. Now, so Berger proved his theorem in 1955. It took another 32 years. So it was not proved until 1987 by Robert Bryant that G2 and spin 7 do occur as holonomy groups. So I believe that until Bryant proved his theorem, that people actually believed that probably G2 and spin 7 couldn't occur as holonomy groups. Okay. So let's now have section 2.5 on a discussion of Berger's list. So there's a way I find useful to explain the list, which kind of gives you a pattern to it, which is to explain it in terms of division algebras. So it is helpful to think about Berger's list in terms of the four division algebras. So a division algebra is, well, it's a real vector space V with a 1, an identity, and a norm, a usual kind of bilinear norm, and a multiplication such that the norm of A times B is the norm of A times the norm of B for all A and B in your algebra. And maybe you want the identity to act as identity. I'm not sure how important that is. But the multiplication is not required to be commutative, associative, anything like that. It's just required to be multiplicative. And the four division algebras are, well, the reals, the complex numbers, the quaternions, and the octonions, or Cayley numbers. So these are the the quaternions. These are called the octonions. They're also called the Cayley numbers. So invented by William Cayley. So these are perhaps less well known. So as you go down the list, you double the dimension. So C is R squared, H is R4, the octonions are R to the 8. And each time you go down, you kind of lose a property. So, well, the reals, they're ordered, and they're associative and commutative and so on. The complex numbers, they're not ordered, but they are commutative and associative. The quaternions, they're not commutative. But they are associative, and the octonions are not associative. And well, lack of associativity actually screws up an awful lot of things. And then the final property you lose is existence. So the next thing on R to the 16 doesn't really exist. Okay, so I'd like to list my holonomy groups in. Okay, so okay, I'm going to go down here, add things to the right. So I'm going to cheat by including O of n first, which is the holonomy group of generic metrics on a non-orientable Riemannian manifold. So this is excluded from Berger's theorem because of the simply connected assumption. But I'm going to put it in anyway as a to make the pattern look a bit nicer. Then SO of n, U of m, SUM. I'm going to put SPM, SP1 above SPM, and I'm going to put spin 7 above G2. Okay, and then these guys act on O of n acts on R to the n, as does SON. U of m acts on C to the m, as does SU of m. SPM, SP1 acts on H to the m, as does SPM. So spin 7 acts on the full octonions, which is R to the 8, whereas G2 acts on the imaginary octonions, which is R to the 7, and you can think about that as living inside R to the 8. Okay, so the way I've written it here, we've got two holonomy groups for each of R, C, H, and O, although O is different because they don't appear in a series. So here, the second thing is with determinant 1. Over the reals. These things are with determinant 1 over the complex numbers. These things are, well, in some sense, with determinant 1, although that makes less sense. Well, here I'm thinking about the determinant 1 as being cutting out this SP1 factor. Okay, I'll tell you that in a moment. And then the final thing, you can think about this as in some sense having determinant 1 too. Okay, so the okay, so this here is, well, it's really a holonomy group of generic metrics on non-orientable manifolds. Okay, so sorry, before I answer your question, so we at least, well, roughly get two holonomy groups for each of R, C, H, and O, where one with, in some sense, determinant 1. Okay, so the octonion case basically it doesn't work in 8m dimensions for m greater than 1, because basically O not associative means there's no good notion of a kind of vector space over the octonions. So if you try and define a notion of vector space over the octonions, you'll find that when you try and classify these guys, they'll have actually a natural decomposition into a direct sum of single copies of the octonions. And you can't have kind of, well, if you say, well, you want a group of matrices over the octonions, and then you try and when you multiply them, you won't get a group because the group multiplication is not associative. So basically, the reason why we don't have a repeating pattern of things in dimension 8m for all m here is the non-associative of the octonions is kind of broken the pattern. Okay, so as to how SPM SP1 acts. Well, so SPM is basically the group of m by m matrices over, well, let's say A over H, so quaternion matrices, such that A times A bar transposed is the identity. So this is more or less the usual condition on orthogonal or Hermitian matrices. So bar here means you take the quaternionic conjugate, which well, it takes 1 to 1 and I, j, k to minus I, minus j, and minus k. So now we take h to the m is column vectors q1 down to qm with the qi in the quaternions. And then okay, so SPM cross SP1, which is not quite the same thing as SPM SP1. This acts on h to the m by, well, so if we take aij for I and j is 1 up to m in SPM, and b in SP1, so b is just a unit quaternion. So this is going to take the column vector q1 down to qm, gets mapped to b times q1 down to qm times the matrix aij. So we're using matrix multiplication over the quaternions. Okay. Now because quaternion multiplication is associative, this behaves well. It doesn't matter which order we multiply these three things in. But the quaternion multiplication is not commutative. Okay, so that means we can't take the constant b through here and incorporate it into the a. So if we were to do this with the complex numbers instead, so for u of m or whatever, then if we multiplied on the left by a unit complex number and on the right by a matrix, we could take that would be the same as we could take the unit complex number through here and multiply it into the matrix, and so it would be all the same as right multiplying by some matrix. So you don't get a kind of u1, u of m, or whatever. But in this case, because quaternion is not commutative, we can't move the B through. So this acts on here by this, and if these are kind of quaternion unitary, they satisfy this A transpose identity, then this preserves the metric on H to the M, and therefore gives you a subgroup of SOM. Now, in fact, minus the identity minus 1 acts trivially, because if B is minus 1 and A is minus 1, then it doesn't change Q. So then by definition, SPM SP1 is equal to SPM times SP1 divided by the normal subgroup, which in fact is the centre, minus 1, well, and 1, 1. Okay, so that's how that acts on HDM. In the case m equals 1, this is actually SO4 is SU2 cross SU2 over minus 1, or standard minus 1, which is pretty well known. That the double cover of SO4 is SU2 cross SU2. SU2 is the same as SP1. Okay, right, so, sorry, I've got distracted. All right, so, sorry, oh, sorry. All right, so next, let's talk about how Berger's theorem is proved. So let's go for a sketch proof of Berger's theorem. And this is all going to come down to the connections between holonomy groups and curvature, which I talked about at the beginning this morning. Okay, so let's suppose that X and G is a simply connected and irreducible and non-symmetric Riemannian manifold. Riemannian n manifold, let's say. And let's say that the holonomy group of G can be some big H, which is a Lie subgroup of SON. So the question which Berger is asking is what are the possibilities for big H? And the answer we want is that the only possibilities are those 7 things in Berger's list. Okay, well, so a few things we know. Firstly, as X is simply connected, power 1 of X is 0, or 1, we know that the H is connected. And also, as G is symmetric, the representation, irreducible. As G is irreducible, the representation of H on R to the n is also irreducible. That is, R to the n does not split as a direct sum of two other non-trivial representations of H. Okay, so actually we can now use, so it is a fact from the theory of Lie groups that or representations of Lie groups that are connected connected Lie subgroup of O of n, which acting irreducibly on R to the n is closed in SO of n and hence compact. As SON is compact. Okay, so therefore H is a closed and connected Lie subgroup of SO of n. Right, so what Berger did is he made a list of all closed and connected Lie subgroups H of SON for all n acting irreducibly on R to the n. So this was of course an infinite list and a kind of infinitely complicated list, so this took him a little while. And this is using Lie group theory. So there's a classification, let's say, of all compact Lie groups using Dynkin diagrams and that sort of thing. And you can also classify inclusions of such things. So you can classify pairs of H sitting inside SON. You need to know what's the Cartan subalgebra of H, and that will sit inside a Cartan subalgebra of SON. And then you need to know how do the roots of H relate to the roots of that, and so on. So this is something which you can tackle using the theory of Lie groups. So then he applied two tests to each group on the list. And these tests are necessary conditions for H to be a holonomy group. So I'll tell you what those two tests are in a moment, if I have time. And then, well, so the only H which pass the test, I think, are those on Berger's list. So I'm a bit confused about spin 9. So Berger included spin 9 in his list. I'm not sure whether it passed the test, but it excluded for some other reason, or whether Berger simply made a mistake. But anyway. So let's talk about what these tests are. So Berger's tests are algebraic and to do with curvature. Okay, so let's consider the Riemann curvature So I'm going to write it R lower A, B, C, D. So I've used a metric to lower the upstairs index to a downstairs index so that I'm now allowed to permute all of these guys. Riemann curvature R of G. So at a single point, let's say, x0 and big X. So then, well, we know that R, A, B, C, D lies in the Lie algebra curly H of the Holomny group big H, tensored with lambda 2 T star x0 of X, where curly H is the Lie algebra big H. Okay, so that actually makes sense for Holomny groups on an arbitrary vector bundle. But for Riemann metrics, the curvature has a symmetry. R, A, B, C, D is equal to R, C, D, A, B. We're allowed to swap round the first two and the last two indices in this. So actually, because it lies in H in the first two indices, it also lies in H in the second two indices. So R, A, B, C, D lies in H tensor H, and actually because it's symmetric like that, it lies in S2 of curly H. So the symmetric tensor product, so this is a vector subspace of H tensor H, symmetric under swapping round the CDs and the ABs. Okay, so it lies in, this is, the Holomny group imposes linear restrictions on the curvature. The curvature tensor is forced to lie in a vector subspace of all possible curvature tensors determined by the Holomny Lie algebra. So next we bring in the Bianchi identities. So also the first Bianchi identity gives that R A B C D plus R A C D B plus R A D B C equals 0. Okay, so R lies in this vector subspace of all curvature tensors and it satisfies that linear equation. So let's write that as a equation star. Now let's write curly R upper H for the vector subspace of the vector space S2 of curly H, well, of, let's say, R in S2 of H, satisfying this equation star. And well, for many possible subgroups big H in SON, then this R big H is small, or even 0. So we're intersecting a bunch of vector subspaces in the vector space of all curvature tensors. Now, if H is small, if it's a small vector subspace of SON, if it's got large codimension, then this is a very small subspace. You intersect it with a set of things satisfying that symmetry realization condition. Quite often you just get 0. Okay, but then getting 0 would tell you that basically H can't be a holonomy group because it's going to contradict the Ambrose-Singer theorem. Okay, so however, the Ambrose-Singer theorem implies that, for big H to be a holonomy group, it is necessary that, if we look at the set of all R, A, B, C, D times V upper C, W upper D for R, A, B, C, D in R, curly R, H. So we're contracting these with one copy of H, which is the CD indices. This is now a vector subspace of H, and this is for all V and W. These should generate the Lie algebra H as a Lie algebra. So sorry?
Do you need all sorts of parallel transports?
Yeah, but this vector space is a vector space of all possible, it contains all possible parallel transports. So the parallel transports from every other point also satisfy the conditions which were used to define this vector space RH. Okay, so this is Berger's first test. So if, for example, H has non-zero Lie algebra, but curly RH is a 0 vector space, then this thing is a 0 vector space, it doesn't generate H, and then you can throw away H as a possible holonomy group. Okay, I think I'd like to run over again by a couple of minutes and just tell you what Berger's second test is. And then stop. Okay, for Berger's second test, note that, the covariant derivative nabla E of R, A, B, C, D lies in, this derivative, the E index, gives us a factor of R to the n star. And then the R, A, B, C, D part lies in our funny vector space curly R, H, and the derivative also lies there. So this lies in this vector subspace of derivatives of curvature tensors, and it satisfies the second Bianchi identity, which involves symmetrizing over, well, cyclically permuting over E and C and D. So nabla E, RA, B, C, D, plus nabla C, RA, B, D, E, plus nabla D, RA, B, E, C, is 0. Let's call that 2 stars. Okay, so, well, for some H's, the vector subspace of elements of R to the n star tensored with curly RH, satisfying this second Bianchi identity, 2 stars, is 0. Okay, so that forces, well, if so, then you have nabla of R is 0 and G is symmetric, or at least locally symmetric. And conversely, which contradicts G non-symmetric. So then Berger's second test is that this vector subspace should not be 0. Okay, so let's say this is Berger's second test. Okay, well, so these days, anybody born after 1980 is taught from the cradle how to compute things using Mathematica or Maple or whatever. Berger was doing this with kind of sealing wax and bits of string and things, and so he was doing intersections of components of things in 1,000-dimensional vector spaces with a more or less a quill pen and a bit of paper. So his thesis was really a triumph of computation. I've endless admiration that he actually got to the end of this project in a finite time. Anyway, okay, so let's leave it out there. Do you want to have a break, or should we just ask some questions and then go and have lunch?